For example, Golang has some level of a concurrency model that differs from other languages, and for that reason, a lot of people love Go for APIs or web applications that are going to be moving around lots of data, but is more robust than, say, JavaScript. On the other hand, we can look at other languages that are isolated. When you would want to learn an isolated language is typically if you have a very isolated purpose for your application, or if you're a developer and you want to get paid. Because a lot of times companies will create startups and they'll use these isolated programming languages and then find themselves in a hiring crisis because, there aren't a lot of programmers who program in Kotlin. So because of that, they have to choose the best bidder that they can find, which might be a more expensive developer compared to a JavaScript developer who doesn't know any Kotlin. So if you're a developer, learning a more niched programming language might be the thing for you because it keeps you suitable for high-paying jobs. It also keeps you relevant as long as the programming language stays relevant. However, if it's a more niche language, it might die out. So then you risk having to learn a new language to be able to stay relevant. So next we're going to talk real quick about types, annotations, and then I had test-driven development thrown in here. I actually took it out because that is a whole topic on its own, which is really cool, and we don't have to get super deep into it today, but I can briefly cover it. So types are basically the way that we classify our data. We say, hey, this is a number, this is a float, right? Or this is a string, this is text. And we go from everything from text and numbers, which are super basic, to more complex data structures like arrays, maps, hashes, etc. And our way of being able to detect errors preemptively based off of types and other properties is called linting. And the reason I bring this up is that it's really important to include typing and linting into your application because it gives us a structure, a defined structure for how our application works. So, you're building your application. First thing you want to do after choosing a programming language is choosing how am I going to structure my code. And so that's declaring these are the types that I'm going to use. And I've tried programming without types. It's radically more difficult to program without types than it is to program with types and linting. Because when you have types and linting, you have a check that says, hey, this doesn't match up with how it's supposed to be. That's really what it is. You assign types, you say, this is supposed to be a number. And if you don't get a number, you get an error. And so because of that, you can catch errors early on. So the importance is type safety, ensuring that operations on data are valid and that they are returning or interacting with the same data in the right way. Readability, it makes it easier for programmers and developers to understand. Consistency, it speeds up the programming by catching errors early instead of, your program crashes and you have to go through lines and lines of code to figure out what's wrong. And then compatibility, making sure that in a multi-application system, each application can communicate effectively. And this is what a multi-application system looks like. We'll talk about architectures in a moment. But essentially the example here is that we have a front end and a back end, and they have to communicate. And if we didn't set up types in the right way, sending the wrong data in the wrong format, which we don't know what format it is because we don't have declared types, could catastrophically ruin things where, hey, maybe we have an error on the back end. Or even worse, a hacker who has the front end exposed could send data and inject it into the back end that wasn't expected because we weren't typing and we weren't making sure that the data came in the right types and checking that. So in a multi-application system, it's important to declare, hey, the back end needs a user data with maybe a name, an email, and an address, right? And then in the back end, it'll be expecting a name, an email, and address. That's essentially what typing is making sure the two can be in communication and correspond in what they receive and what they send. Annotations and formatting are similar. Annotations are metadata that we provide in our code, and it allows us to basically annotate or give notes on what we're programming. This could be used for automatic documentation. It could be used for clarity for developers like myself to be able to analyze. And then not just that, but formatting, how you indent your code, how you organize it, how you structure it is also important, because two developers look at code completely differently. You know, how I look at code might be different how you look at code. So annotations and formatting, setting those standards early, really important when you're building a product. And so the importance here is clarity, tool support, so like TypeScript and other linters out there will check to make sure that code is properly annotated or formatted. And then you could also do, you know, auto completion and auto error detection. This gets us into test-driven development, where test-driven development is where you define tests before you program and check to make sure that the programs return what you're wanting them to do. The cool thing is I recently met somebody who, another developer who, he built an AI that will build based off of a test. So you build the test, you build what you want the program to return, and then the AI will go ahead and work on the inner workings to make sure that it returns the right thing. And it's this iterative process. And I don't know how foolproof it is. It sounds like an awesome concept, and it's something that I aspire to build eventually as well. But test-driven development can go really far, especially today where we have, you know, ChatGPT or GitHub or all these different AIs that can go ahead and help us with our development. But then annotations and formatting also helps with documentation and collaboration. It makes our process more efficient. So now we're going to jump into application architecture. This is my favorite part because I find it very fascinating how we structure our projects and how we decide to structure our products. So the first application type is just a monolith. This is your basic Flappy Bird app where it doesn't really do anything but store maybe your high score. And so monolithic apps don't require many external dependencies. They don't have a dedicated backend. They're more just an application that's standalone. You download it and you update it by downloading a new one. So in a monolithic application, all of our dependencies and assets are linked to the application, and then maybe we query for some external resources, maybe we check a database, or maybe we check we send like an API request every now and then, but it's not to the point where we have to dedicate a backend to it, and it's not to the point where we have to dedicate a security level behind the monolith to protect any data or anything like that. Next, we have front end and back end. So front end and back end is your typical run-of-the-mill solution where you have a back end that acts as a security wall between important data that the front end needs to access. So the front end basically is everybody can see it, right? Anybody and everybody has access to the code in the front end, and they're able to see directly into the resources and that the back end gives it. However, the back end acts as a protective layer that will go ahead and request data, will go ahead and request resources, will go ahead and send or receive data, and it acts as that layer in between. This is when you set up a login feature, right? You want to have a back end ready to be able to accept logins and save passwords, but you don't want the front end seeing all of the passwords, right? You'd store the passwords in a database, and you'd make sure that only the right user in the back end can retrieve the data. And so front end, back end, super typical configuration. This was more common back when people were using virtual machines instead of containers, because the difference is that virtual machines, they are a virtual operating system. You basically wrap your application inside of you put it inside of a virtual operating system. So you can have multiple operating systems on one server, and each one of them is responsible for running one program. Now that's really not very resource effective, right? That's very resource intensive because you have to have a separate operating system for everything you deploy to a server. It's kind of ridiculous when you think about it, because here we have our virtual machine, and you can see it's in parallel to multiple other virtual machines. If you think about it, each one of these has to run Linux. And that's a lot of Linux instances. That's why we have a lot of really lightweight Linux distributions out there, so that we could deploy them in this way. In steps containerization. What containerization allowed us to do is it abstracts a virtual machine and it says, hey, as long as we have the right container runtime, we can run containers or packages within a single virtual machine or a single operating system. So the abstraction here is that imagine like a shipping container and you pack it full with your program and then you deploy it. You can essentially have multiple shipping containers in parallel on one virtual machine or one operating system. Makes it way more efficient because you don't have to have multiple operating systems. Instead, everything is isolated in these containers, and they can be delivered in a portable way and run in a portable way, but it's not reliant on individual operating system, individual operating system, individual operating system. So containerization's a better scheme when you're building an app that has to communicate with other apps. It's also better in the case of you want to have a portable app. So if you're a startup owner, I recommend you asking your development team, hey, how is my application orchestrated so far? Like, do we have a front end, back end on a virtual machine? Virtual machines can be more costly to deploy, especially in like a cloud situation, a cloud instance, right? Versus containerization, that's the most common way these days, is we containerize our applications. It's a lot more efficient and it's a lot more cost effective. Next is microservice. Microservice is where we have multiple containers and they communicate to each other. So the benefit of microservicing is that now we are taking each part of our program and we're containerizing it independently. So you can run multiple microservices kind of together. So let's say you have a login feature. You can deploy the login feature separately from maybe a monitoring feature that monitors data in and out, right? And the benefit here is, let's say you have a team working on the login system and you want to update it, but you don't want to crash anything in the monitoring system. Those two pieces work independently of each other, so you can update one and you don't have to update the other. And it leads to shorter update times, it leads to quicker changeover, it leads to a lot of efficiencies that you don't see in a front-end back-end program or even just a single front-end containerized program. Any questions so far?
Yeah, I'm just curious. Okay, once you have some like containers,
Yeah.
and you have different parts of the program,
Mhm.
is there some type of IDE or something like that you use to separate, or you can just continue on IDE and it goes into like Docker or that for you?
Yeah, so there's Docker, right? Docker's the most popular container runtime. Essentially, Docker will go ahead and give you the tools to isolate, to containerize your application, and to run it. And then you have orchestration. What orchestration is how you define how you run your containers. So it's saying, hey, this container is going to run in parallel to this other container, and it's going to connect together in this way. You're going to connect this port to this port. And it's how you launch, deploy, and scale your containers. So Docker has Docker Compose for orchestration. It's part of the Docker ecosystem. And then there's also Docker Swarm, which I believe is an abstraction on Docker Compose. However, the most common orchestrator is Kubernetes. And you hear Docker and Kubernetes used a lot together because Kubernetes is more production grade versus Docker itself, Docker Compose, is more just I'm testing it on my computer. And so this is like almost a whole nother talk on of itself, and it's a good idea that I should do one on containerization because it's something that you could get really in depth with. But any other questions? Okay, sweet. Anybody else?
The microservices usually communicate through HTTP, right?
Yeah.
But they could communicate with RPC,
I'm not familiar, but I can tell you that I've set up microservices before with like TLS and like other protocols, and the reason why is I was working for a DoD contractor, and we were testing out how these microservices run on a firm machine that isn't connected to the internet. So you can run you can connect microservices together with other protocols, not just HTTP. Yeah. Anything else? Sweet. Now we get to my favorite case. It's called serverless, and the reason why it's called serverless is that we don't use any dedicated full-time running servers. What serverless computing is it's using our cloud resources on demand. So the issue with spinning up a container or running something on a virtual machine is that you have to dedicate it to be running on a server space perpetually. And the reason why is that you need it easily accessible when somebody wants to log in or when somebody wants to access it. So you need it right there at the forefront. Serverless, on the other hand, breaks down our containers and our containerization process on a very small, refined level so that it's more like each function has its own container instead of it being more like each application or macro level of the application has its own container. So we're breaking it down into kind of really refined components, and it's really nice because cloud providers like Amazon will not charge you for the downtime that your micro containers will have when you're not running your program. So the use case here would be a basic CRUD app. It's like create, replace, update, and delete, which basically means, let's say we have a application where we have users, let's say it's a daily diary, and it's password protected. You use username and password, and users store in their notes in the daily diary. Well, all you need for that kind of app is you just need the ability to send in data, retrieve data, and secure data, so secure it with a password and a username. And so that basic kind of app we can do serverlessly because we don't need a database constantly running. We can use a serverless database or a NoSQL database, like MongoDB, or I believe DynamoDB is AWS's equivalent. And we can hook it up to our serverless function, or what AWS calls a Lambda function. And what these functions are is they're just micro containers that run only when you request them to. So you could write a function that says, hey, go fetch me this data. And all you do is you just run the Lambda function that will fetch the data, and it will retrieve it, and there's no downtime cost. It's only the uptime that your little function is actually running for that costs. And then you could create another function that says, hey, go delete this data, and it'll just trigger that function. And so it's super effective when we're talking about, hey, I want a simple app where I can retrieve and submit data back and forth. Super simple, best situation there. So here the example shows you we have our functions. We have a load balancer that just balances who comes in and who comes out, how many of these functions we need deployed, and that's built in to our cloud provider typically. We have the gateway, which is how we configure our API. So an API is just the communication tool between two applications. So maybe between our front end and our functions here. So you would configure your API to be able to leverage and access our functions, and then our functions have access to our assets, like maybe a database, or maybe a S3 bucket, right? So AWS's S3 bucket is just their simple storage solution, their simple object storage. And so maybe you have your external resources and assets on this other side, and they're all hooked up through the cloud, which is super simple and great to develop with. So lastly, before we finish up with our architecture discussion, we're going to real quick talk about architecture diagrams. What are they? Why are they important? So architecture diagrams, they're basically just flow charts and any kind of diagram, high level or low level, that illustrate how our application works. This is something where if you are a startup owner or you are a project manager, it's something that I would request of your developers and engineers is please make me diagrams. The reason why is that when your application changes hands, let's say you need to fire somebody, all of that knowledge about how that application works lives up in our heads. And what do you do if you fire somebody or they quit on you? you can't extract the knowledge from their heads unless you already have it documented. Architecture diagrams are the easiest way to pass information from one developer to another. Of course, code comments and annotation helps. But being able to show somebody a diagram and say, hey, this is how these systems communicate and work, and these are the types that are exchanged between them, that's amazing. It takes you one step further. So why are they important? They help with clear communication, better planning and decision making. You can look at the top level resources and say, hey, what do I have to move around? What do I have to reconfigure? And then they also help with efficient development and onboarding. So being able to onboard other developers and make it more effective to develop with. And so these are some examples of some architecture diagrams I've created. This is Sprouty. This is a tree-based, the idea was it was a tree-based data system where we were storing data in a tree model. So it was kind of like a graph-based database. However, we were implementing everything ourselves and working with different nodes and then having basically parent nodes down to descendant nodes and then being able to link them in kind of a botanical fashion. So here you could see we have a lot of notation on here. You can see we have our backend manager here. We have our front end that communicates with the backend manager. And then we have different microservices here. And our microservices are written in Go. These are the different main components of our microservices. And these are kind of like, maybe a file of code or maybe a folder of code. And then over here we have other components. This is a diagram here showing how the tree is structured on the back-end side in the core microservice, and this is how it shows on the front-end side before we've opened up the tree all the way. So you can see here it's very explanatory on how this works, and with more detail I could fill you in on how this whole project works because we have a diagram shown. Similarly, this is another app I created. This was one of my first apps. I came out after coming out of college. I tried creating an application called Shot Glass Jobs, which basically uses AI to data scrape LinkedIn or Indeed and find listings on there and for jobs and then be able to compare them, use AI to find you the right ones, etc. That one ended up getting difficult because AWS and it got to my servers started getting blacklisted on some of these websites because Indeed would find out, hey, look, he's kind of going through our system and data scraping. They were able to notice that. So I put that one on hold. But as you can see here, I have the whole setup shown. You have Cognito, which is used for authentication. You have DynamoDB, which is used for holding data. You have your Lambda, which are your serverless computes. And then we have our whole system for front end on the side here. And this is really high level. This is just showing, hey, these are the basic tools that we're using. And this is how it lives in our ecosystem. And then real quick, I can show you, I was just working on one right now. My company, Circle Square Labs, we have an R&D department and we're working on SwiftSend, which is a messenger system similar to, maybe you've heard of Mailgun or you've heard of a couple of those. Essentially, we want our own internal messenger system sending through Amazon SES. And this is basically just how we're orchestrating it and hooking it up to our application, which is our client dashboard, Odin. So this is another diagram that I'm just working on the go, and so I'm always building these whenever I'm planning applications because they help me understand, hey, this is how my application works. And if I need to change something, they also help me figure out, hey, we need to replace SES with something else. How does that affect our program? Well, if we replace SES, we also have to replace SNS, and then we go down the list, right? So super effective. So before we take a water and bathroom break, we're going to talk about cloud services by use case. This is basically how do we use our cloud services effectively to be able to get us to our architecture goals. So the first use case that we're talking about is front end and back end. Because mainly with a monolith, we don't really have to worry about cloud architecture because monoliths are isolated. They just use, framework, programming language, you just program it out, and then you deploy it somehow. So when we're talking about front end and back end, Typically, we're talking about hosting and scaling web or mobile applications with a distributed access to the front end. So being able to connect into that front end, and then a back end. And so for this, you need static site hosting, so being able to host your application. A lot of services like AWS Amplify or Firebase allow you to do that. My favorite is Vercel, just because it's free and it has a really great interface, super effective. So this would be for your general web application or your mobile application, just to host it. Mobile application, not so much, mostly anything that runs on a browser. And this is specifically for front-end hosting. Then you need content delivery. Essentially, all of your front-end code lives on a server somewhere, and you want to get it out to your user as fast as possible. So to get it closer to them, you can hook it up to content delivery systems like CloudFront, which will go ahead and put it on servers closer to your users. So it'll distribute your data. The next use case is back-end hosting. And that has to do with hosting our backend code either on a virtual machine for custom servers. That would be like EC2, which these days largely runs a lot of more on the containerized end of programs. They kind of containerize it for you, I believe, at Amazon. But virtual machines or Azure's VMs, which is their actual virtual machine compute. Google has their compute engine. And so essentially this is us deploying our application to run full-time on a server somewhere. And then when somebody needs access to it, say you have 3 parties try to access it, you can put in scaling protocols to increase the number of those servers being accessed. So basically you hook them all up together. And then we have real-time backends. Real-time backends are really interesting. Firebase real-time data space is a good example of this. It's a backend that doesn't really have a full backend connected to it, but it more just has a live database and real-time data processes that can occur in real time. So it's like if I need to communicate to another user, I need that to be sent in real time. It would be done in a similar fashion to a real-time backend. But this is only for extreme cases where you need your data updated immediately whenever you update it. Next, we have containerized applications. For containerized applications, we typically use Docker or Kubernetes, Docker and Kubernetes. Docker being your containerization runtime and Kubernetes being your orchestrator. But there are other ones out there that exist. For cloud services, when we're deploying containerized applications, we have EKS for Kubernetes, which is on Amazon, or AKS, which is on Azure, GKE, which is on Google Cloud. These are for orchestrating Kubernetes-based containerized applications. So that's if we're orchestrating the application with Kubernetes. If we want to manage our containers without Kubernetes, but we want to manage them with the cloud platform's system, we can use ECS, which is Elastic Container System, Azure Container Instances, or Google Cloud Run. And this allows us to manage and oversee the lifecycle of our containers with cloud computing resources, instead of having to come up with Kubernetes logs and all of that. Now, the drawback of using a container management system from a cloud provider is that you have cloud provider lock-in or vendor lock-in. That's essentially where these cloud providers get you between a rock and a hard place, where you're kind of stuck because, hey, look, I built out this whole application, this whole system, but I built it out with ECS, Amazon's container orchestration, so I can only run it on Amazon. So if you need to, say, move it to Azure, you can't do that because it's orchestrated with Amazon. So my recommendation is always to use Kubernetes as the orchestrator so that you can move it to Azure, because it gives Azure all the information for spinning up and running your applications. And then we finally have registries. This is where it's a repository, just like GitHub or GitLab, where we store our container images. So this is where we dump our container images and developers can download them onto their systems. Cloud services can pull them in and spin them up. So registries is where they live. And Docker Hub is a very popular one. Amazon has its own Elastic Container Registry, and then Google has Google Artifact Registry. Next, we can talk about serverless applications. For serverless applications, all you need are compute services. So compute services allow developers to run code on a very small level. And so this is, a microservice. And AWS's version of that is Lambda. Azure's version is functions, and then Google Cloud's version is also functions, called functions. And so serverless compute basically allows us to run our applications on a micro scale on the cloud. And it's on demand, so you don't have to pay for the application to be running permanently. And so finally, we have API gateways. So API gateways allow us access into our applications. They're not just for serverless applications, but they're most commonly used with serverless applications, where it allows us to have access to our application and communicate with it by, setting up an API request and requesting data and getting data back. Our next use case is user authentication. This is for our sign-ins and access control. I really like AWS because they have such strong access control. You can set up access control where only specific users have specific privileges. However, it can get very, very complex. So there are a lot of different applications for user authentication. If you need a more robust and focused and really nitty-gritty user authentication system, I would recommend AWS Cognito. But something that I've been toying around with lately is Supabase. Supabase is a database with a user auth or a authentication database or table. And essentially that allows you to store user data and protected data. So user authentication refers to how do we protect identities, how do we protect usernames and passwords in a database. And so these are usually separate databases or separate tables that are isolated and have very strict policies for in and out. And so you can use AWS's or Firebase's authentication applications. You could also use something like Supabase, which is a little bit easier to set up, more developer friendly. And then we also have third-party authentication applications, kind of like Auth0 or Okta, which both allow you to communicate and log in with different external providers. So for example, you're logging in with Google or logging in with Facebook kind of deal. Next, we have data and databases. When we're breaking it down, we have three different kinds of data. We have objects, we have NoSQL data or documents, and then we have relational data or tables. Object storage works to submit, media or firm objects. This could be your PDFs, this could be your images, and that's how you store them. And so AWS has their simple storage solution, Azure has blob storage, Google Cloud has Google Cloud Storage. All of these are different tools for storing big documents or big media. Then we have NoSQL document storage. This is SQL-less, meaning that we're not storing things in a table format, which is the mark of relational SQL databases, but instead we're submitting them in JSON-like documents. It's basically flexible ways to store our data. And then finally we have relational databases, which is firm structures in tables. So it's table-based data storage. And if you're not super familiar with these policies, again, this is something that you can talk to your developers about or read up about online. Essentially choosing a relational versus a non-relational or a NoSQL database has to do with how are you storing your data and how often are you going to have to nest data inside of each other, right? So with NoSQL databases, we have a lot of nested data because we create rich objects that don't have a specific structure. Versus with relational databases, we have a specific structure, so we can't exactly nest objects. Instead, we have to compare and join them together. So these two are kind of two opposing frames of thought. NoSQL databases are typically in the realm of serverless. And then relational databases exist on a server. So you have to run relational databases 24/7 versus NoSQL will store your data in the form of media objects. And anytime a user wants to access it, they'll just query for that media object, that document object. So again, if you're working with a serverless application, NoSQL is a good way to go. If you have a servered application, you probably should run a relational database. And I think we have 2 more use cases. There's a lot of cloud services out there, so don't get too overwhelmed. I'll open it up for questions afterwards, and then we'll take a break. But the next use case is monitoring and logging. This is important when we want to see how many resources our application is using. It's also important when we want to have observability into how our applications are being used. So a lot of the platforms already have monitoring and logging built in through AWS CloudWatch or Azure Monitor or Google Cloud's Operations Suite. This is really great, and this is something that developers should be setting up. And the reason being is that it helps us understand how much compute time, how often our compute time is being used, and by what user, by what processes. It's how we create efficient applications. And then we have third-party solutions. My favorite is Prometheus and Grafana. Super beautiful dashboards, and basically it can show you you can set up metrics that can show you different numbers or metrics associated with your application. I like setting up Prometheus and Grafana for AI because you can see your AI processing through the metrics that you set up. So I like connecting it to, we have this many features, this feature is getting activated this amount of times. So being able to track feature activation and how frequently our features are used is really important in AI, and it helps with pruning and the efficiency of our AI system in the long run. Prometheus in this case is a database that allows you to submit and send it real-time data. And then Grafana is a graphing dashboard system. And I might be able to show you all an example of this after we take our break. I just got to find to see if I have like a picture of it running. And then finally, last use case, we have machine learning, AI, buzzwords these days. Essentially, all of these cloud services have ways for us to manage the machine learning lifecycle, whether it's data preparation, training, and deployment and monitoring. This is AWS's SageMaker, Azure's machine learning, and Google's AI platform. I haven't really messed with these. I typically just build and deploy containerized AI models. But they're more useful in the case where you're building a really large scale AI model and you can't just host it yourself, super simply, right? Something that kind of exceeds containerization or containerization that you want to manage. And so great use cases if you are going above and beyond with your machine learning and AI. All right, we're going to take a quick break. Does anybody have any questions? Sweet. Let's take a 10-minute break, and we'll get back at let's say like 8 o'clock. Just grab some water, use the restroom if you need to, and feel free to chat.
applications, but this whole thing is being recorded by Apple Factory, and you'll be able to find it online. If you join our Discord channel, you can all find it.
Your presentations on
Yeah, these being recorded as a camera right there.
Okay, cool. I like that.
Yeah, I feel like these are helpful topics. A lot of this we presented during our 12-week Foundry Bootcamp program, and the things I recapture a lot. It's just like, hey, I want to build an application. How do I start? Where do I start? And rarely are you able to, like, all these options are laid out in front, right?
Yeah, just wanted a little bit of
I mean, clouds are dynamic, instead of something real quick, it grows, kind of uses the scalability. So are you going companies and hybrid, things, or anything they want? Let's keep you applying.
Most of my clients are startups that want to build an application, but we don't know where to start. I work a lot in the startup realm because it's easiest to find clients that are Austin or startups. Because they're either looking to offshore their development, and they need like a project manager to be able to help with the offshoring process and offshore development. And I've got connections out there where I can hook them up with offshore developers, and then I can manage the project. Or they're looking just to bootstrap and use $1 or $2 to build their stuff to actually build out the next thing.
So they come with high level diagrams or what kind of business requirement and all that.
Yeah, sometimes it's not even a high level diagram. Sometimes it's just, this is my idea. And then we go back and forth over a million calls. And then of course I always try to get them to create diagrams like those right box too, and just that communication too.
You're closer to.
But I love what I do. It's cool because every project's different, right? Like I've worked for DOD, I've worked on motorbikes, electric motorcycles, I've worked on dating apps. Like I've worked on a bunch of different projects on different.
But the client is in Austin or is it like all over the place?
Most of the time it's in, everybody I've actually worked for mostly been out of Austin. My first job was based out of Colorado, but that was a remote one. Yeah.
Because it's a successful company, you learn about growth. But some companies,
Yeah, tons. Not one that I started from the ground up, but a couple, like I've worked with Rocky Fit, which is they do like fitness apps, they build fitness apps. And then I worked with Checkmate, which is a dating app. And then I've also worked full time with like a DoD-based company, and that was through Foundry and all that stuff. And that's kind of what got my own logistics. So I want to build a company that has both an R&D section and like real true section that works.
Whatever it is.
And then I want to be able to license the technology that I generate for that. That's another one spot is that all of our R&D attempts or efforts go towards real applications of these licenses. Okay.
We're going to hop right back into everything, talking about career paths in tech. And so this is more for people who want to get hired. If you're looking to get a job in tech, this is really important. But actually, as a hirer, as a company that's looking to hire people, you should also know what they should have on their resume, how they should present themselves, and the frames of thought in that. So when we're talking about tech career paths, we're talking about, hey, I am a developer. What kind of developer am I? Am I a front-end engineer? Am I a back-end engineer? Am I DevOps? Am I machine learning? These are all terms that we use, and a lot of people use them kind of interchangeably, especially less experienced engineers and developers will advertise themselves as one way or another, or maybe they'll switch it up based off of what company they're applying to, but they might not have expertise in these areas. So the first one is front-end engineer. Front-end engineers have core skills in HTML and CSS and JavaScript, so how they build web apps with those tools. They know the basic frameworks and libraries. Typically React is the most common one, but there's also Vue and Angular out there. There's also, if you know Dart, you can build with Flutter for different kinds of apps. And then responsive design is a key skill for a lot of these people, a lot of these engineers. And then they typically are working with how does my application scale from a desktop version that you can open up on your browser to a mobile version where you're on your phone. And I'm sure that a lot of you all have seen websites that just very poorly scaled, right? It just, maybe you put it on your iPhone and it breaks, or something pops off the page and you can't find it, etc. So responsive design is very important. And then finally, having a knowledge of version control and build tools, knowing how to, submit to GitHub, build with Webpack, Babel, Node Package Manager. All of these are really important tools to know as a front-end engineer. And so what should you highlight on your resume? You should highlight a project portfolio that shows websites or web applications that you've successfully deployed. And that's super easy because all you have to do is provide a link, right? And you can show what you've built with. User experience, so being able to connect maybe a Figma account and have some Figma prototypes on there, or be able to show some images of some UI designs you've created, the differences in accessibility and performance, and being able to show your responsive designs versus your desktop versions, very important. And then showing cross-browser compatibility, so how your applications work on different browsers, for example, Firefox versus Google Chrome, that's very important. And so being able to write those up, my favorite way to write that up is in case studies. So on my portfolio website, I have case studies for all the projects I've done. Some of them aren't on there because some of them were, classified or, under a agreement where non-disclosure is important. But having case studies and being able to show, hey, I worked on this project, and this project I did this, and this is how I accomplished it, and these are the examples, this is the website, this is what I built. That's really great for when recruiters are trying to hire you, because you show them that and it shows proof of concept. Backend engineers typically have core skills in knowing backend languages like Python, Java, Go, or Ruby. They typically have a strong knowledge of databases, like relational databases, like MySQL or PostgreSQL, and NoSQL databases, like MongoDB or DynamoDB. They build out APIs, so you'll know things about RESTful services, GraphQL, and webhooks, basic ways for us to communicate between the front end and the back end, or basic ways for us to communicate between two programs. And then, as a backend engineer, you have to know best practices for security. The more you know, the better. It makes you a stronger backend engineer to be able to say, hey, look, we're going to check this and this and this for cybersecurity threats. We're going to set up a DevOps pipeline to be able to make sure that we are checking for cybersecurity issues. Just being able to understand how potential malicious users could take advantage of your system is important. And then cloud services, knowing cloud services like AWS, Azure, or Google Cloud is important as a backend engineer. Not on this list, also containerization could be very helpful as a backend engineer. And that moves more into DevOps and cloud engineers, which we'll talk about in a sec. But just knowing a well-rounded amount of how applications are architected, that's more important, I would say, for back-end engineers than front-end engineers. What to highlight on a resume? For back-end engineers, you're going to want to showcase where you've built APIs or databases or optimized server performance. And so what this basically means is you're going to want to be able to show, hey, in a case study, hey, I got on this project and I made it more efficient by this percentage, right? I made this program this percentage faster. I built this API and I used these tools. So you're going to want to really highlight keywords, key metrics that you were able to accomplish with your development. You're also going to want to be able to show off architecture design. So this is where those architecture diagrams come in handy, because you can show, hey, I created this system and I created it in this way. Somebody looks at some of those architecture diagrams that I showed y'all and they'll be like, wow, you used Go, you used Docker, you used all of these applications or all of these tools. And they'll be able to get a good look at not only do you know what these tools are, but you know how to apply them. And that's the most important part. And then showing optimization in performance. Again, everything in a resume should be metric based. And so what you're going to want to show on your resume is, hey, look, I optimized performance by this percentage. I hooked up an API that had this many users using it, right? Those things are very important because it shows that you know how to build for scale. And then finally, showing off your automation and CI/CD skills. This includes maybe using automation stuff like Puppeteer or Selenium, setting up CI/CD with Jenkins or GitLab or Circle CI. And we didn't talk a ton about DevOps or CI/CD, but that's basically our pipeline from how we basically deploy our code from repository to the cloud. The next position that we're going to cover is data scientists or engineers. The core skills that these people have are these developers know how to program in database languages like Python, R, or SQL, which is for relational databases. As a data scientist or engineer, well, there is a distinction between the two. Data scientists are more on the level of studying trends and analyzing data, whether it's business data, scientific data, etc., versus data engineers take that data and they create applications that will actually maybe extract features or extract data, right? Like in AI or machine learning. Data engineers work more on the machine learning or AI side of things these days versus data scientists do more trend modeling, graphing, etc. And so both use similar programs. R is mainly used in data science versus engineering uses a lot of Python. And then both can have access to databases like SQL. And so another core skill of data science and engineering is data visualization. This is essentially setting up tools like Matplotlib, or even like I talked about Prometheus and Grafana, which allow us to visualize our data in a graph form. Setting up machine learning algorithms and models is also a responsibility mainly of data engineers, and that helps us with analyzing trends and being able to predict trends. So predictive analysis, super important for data engineers. And that's the distinction. I would say data engineers are more on predictive analysis versus data scientists are more on quantitative analysis, where you're analyzing past trends. Data engineers predict future trends. And then having a knowledge of big data technologies and statistics, those are all very important for data engineering. What should you be highlighting on a resume as a data engineer or data scientist? You want to highlight work where you've done predictive modeling, classification, or real-time data analysis. So the projects where you've gotten real deep in the data and you've been able to extract trends, extract predictions, and you have metrics related to those, right? So saying, hey, look, I found a trend that basically predicted that this would happen, or that we were basically making a mistake here, or we classified this data. Being able to show quantification alongside qualification is really important. Quantitative analysis is important to show on a resume, so the ability to analyze massive data sets and be able to extract insights. So break down our data and reduce it to, hey, this is what we can conclude here, this is what we can conclude there, and this is how we're going to respond to it. Super great for your case studies. ML models, so any machine learning models you've built, great for showing on a resume, because these days the buzzword is AI, machine learning. And then collaboration, showing that you've been able to work on cross-functional teams. A lot of data scientists and engineers work very strongly alongside back-end engineers or business analysts. And business analysts don't know the nitty-gritty of computer engineering or computer science. So being able to show that you can explain and communicate that is super important. And then finally, we have DevOps and cloud engineers. DevOps and cloud engineers work with tools like AWS, automation tools like Ansible, Terraform, and Puppeteer, and then CI/CD pipelines like GitLab or GitHub, or I think GitHub has its own CI as well as GitLab does. Essentially, automation tools will allow you to automate tests. For example, Puppeteer allows you to automate the browser. So it allows you to control the browser like a puppet. It's what one of my AIs are based off of, is being able to control the browser and then extract data features based off of the browser's properties or the web page's properties. We use a lot of Puppeteer in that in order to analyze the web page and then be able to compute it and extract features from it that can then be used to predict where data falls on the page. CI/CD pipelines are important for how we automate our deployments, so how we get from the repository where we store our code all the ways to the cloud service where we're hosting our code. And then we have cloud platforms like AWS, Azure, Google Cloud for being able to actually run our code in the cloud up there in that mysterious data center in the sky. And then we have containers and orchestration, knowing how to containerize our applications so that they're scalable and easily deliverable is important, and how to orchestrate multiple containers together, how to scale them so that we have enough deployed so that everybody can access one, or being able to connect them together. Both of those are really important. We also have monitoring and logging. This is using tools like Prometheus and Grafana to monitor how our applications are doing in the cloud or monitor our cloud resources. So showing all of that, super important. Those are our core skills of a DevOps or cloud engineer. To highlight on a resume, you want to show off infrastructure projects, so projects where you've worked in the cloud, cloud certifications. So those certifications really come in handy here, and they can be difficult to achieve, but hard work pays off, and having those certifications are great, and they really give you an in the tech industry. Containerization and orchestration, showing that you have containerized applications and you've deployed them, super important. And then showing system performance, and again, those key metrics, very important. So before we jump into how much does tech talent cost, this is one of my favorite things to talk about, because I'm going to bring up some statistics that I computed myself. But does anybody have any questions? Sweet. Okay, so this takes us off of the presentation and into, let's see, not AWS. Let's see. Aha. So this is a spreadsheet I put together called How Much Should I Get Paid? So this applies to both developers who want to get paid a certain amount, and it also applies to people who want to hire developers and know how much they should be paying. Because a lot of startups and company owners don't really know how much their developers are worth. And a lot of developers don't know their own worth. You can look on, LinkedIn or Indeed and try to, extract data from there, but if you just look at their graphs alone, it doesn't give you the full picture. So the first thing we're going to talk about is how much should you get paid based on what level you are. Oops, I zoomed in too much here. So based on profession. So as you can see here, I have a ton of statistics on different countries, different pay based off of different statistics, and I've basically narrowed it down into distributions. And these come from various sources. What I did was I actually trained my AI model that can go across the web, and I trained it to be able to read, data on ZipRecruiter or on Indeed and be able to extract that data. And then I was able to actually put that into a spreadsheet. So there are 6 different levels in development. You have intern level, entry level, mid-level, senior level, staff level, and principal level. Entry level is, 3 years out of college, or under 3 years. Intern is, of course, you're in college or you're in boot camp. Entry level is 1 to 3 years out of school. Mid-level is when you're 3 to, I want to say 8 years. I have it up here. Yeah, 3 to 7 is senior level. Staff level is 7 to 15, and principal level is 15 to 22. It could go higher than that. Essentially, when you're talking about being a principal engineer, you're distinguished. You are an expert in your field. You're at a big company that's given you that title. You're a special person because you know the ins and outs, and you're a really great person to talk to. If you are approached by younger people or people who are earlier on in their career, they're definitely going to want to hear everything you have to say. I would, at least. If I met a principal engineer, I would want to glean from them. Staff engineers are experts. They know the workarounds of different products. They know how to implement products. And these titles are typically given to you by a bigger company. Senior engineers are more on a smaller company term. Senior engineers are proficient in computer and software, while mid-level engineers are competent and entry levels are trainees. So entry or junior level, you're training, you're still learning, you have a lot to explore. And then intern level, you're just a learner. You're still in education, you're trying to grow, and so you're trying to get your foot in the door. And so where this comes into play is scope. Where does this matter? This has to do with how much of an influence do you have on the application. Interns are support. They typically report to a team lead, and they just do little things like, hey, go program this function. Can you set up this application, or set up this infrastructure? Go do this small part. And they work hand in hand with entry-level and mid-level engineers, and they all report to a team lead. But entry-level engineers work on a task-based scope. So you'll set them up on a ticket. You'll say, hey, work on that ticket, and then come back to me when you're done. Make sure you go and have it reviewed by a mid-level or a senior-level engineer. Mid-level engineers work on a project level. So they look at the project, and they see the project for what it is, this whole scope, and they're able to review tickets. They're able to say, hey, look, this is straying off in this way. We should do this. They give important insights into how the project's performance is going, and they work directly with the team lead, which is typically a senior engineer. Senior engineers are team leads, and their whole scope is the whole team. So they're looking and saying, hey, we have this mid-level engineer who's on task, we have this entry-level engineer who's lost, and we have this intern who's following the lost guy. How do we get the other two on track? And then you have the senior engineer reporting to a manager, and then in addition, they'd also report to a staff engineer who could be managing multiple teams, and that's the goal of a staff engineer. They report to the senior manager, and they manage multiple teams at once. And then finally, we have a principal engineer. They're distinguished. They typically look over a whole organization, and they report to the director or the board of directors in order to report, hey, this is how our teams, our company is going. This is how they're doing. So we can go back to our payment distributions here. You could see these are our hourly rates. This is important if you're a contractor. Interns typically make about, $25 per hour these days in this economy. This was recently updated at the beginning of 2025. So January, I said, hey, look, I need to update my spreadsheet. So I went and I did all the statistics over again. Entry-level engineers get paid around the same amount as an intern, but maybe a little bit higher, around $30, $33 per hour. Mid-level, you get paid around 40, 45, and then senior level, you jump up to about 60, 65 per hour. And then staff engineers, you jump up even higher. You could be up to 90 per hour. And then principal engineers and staff engineers, there's not a big difference between them. Principal engineers are just distinguished. They've been given the title out of honor. And you can see here there's a little bit of like a pay difference. And the reason why is that there aren't many principal engineers out there. So the number of data to actually choose from is lower, meaning that your distribution is going to be slightly skewed because of that. So, you know, it may look like principal engineers get paid less. It's just there's less data to choose from. So you don't have the people who are super high paying all the time on there as well. And then salary wise, you can see entry level, you get paid around 70K. Mid-level, you could get paid up to around 90 is pretty average. I'm looking at this median bar here. Senior level, you can get paid up to over 150K, but the typical is around 120. And then staff level is around 150K, and principal engineering, again, not much of a difference, around 150. And so this is just general for software professions. Our software professions can be broken down into engineers and developers. And yes, there is a difference between the two. And this is really important if you're looking to get hired or you're looking to hire somebody. Engineers are people or they're engineers who have gone through a 4-year university degree. They've been taught everything from super low-level concepts like assembly in C, data structures, all the ways up to how do I implement this into an application. And honestly, when you're in a 4-year degree, you focus more on the nitty-gritty, the low-level stuff than the high-level stuff. But when you get to the high-level stuff, then that's when you understand all of the components of the impact you're making with your application. Developers, on the other hand, typically go through boot camps, associate's degree, or self-taught, self-trained. These developers have tons of certifications, and they're not any less, they don't have any less potential as an engineer, but what they do have is they have a little bit less credibility. And because of that, there's about a 15% pay gap between engineers and developer positions across the board up until senior level. At senior level, it starts to even out. You only have a 5% pay gap. And then with staff and principal level, there's no distinguishment there. There's no difference. Staff and principal level, you just get paid like an engineer because at that point, you've proven that you have the knowledge. So there is a difference between developers and engineers. A lot of offshore development teams work with developers just because it's less frequent in other countries for people to get a 4-year degree in engineering. US has a lot of a high principle of going to college and getting a 4-year degree, and so it happens more often that you'll find an engineer here. However, engineers do cost more and they do expect more typically when you're hiring them. And so those are the statistics there. How much you pay also depends on the profession that you actually claim. Being a general software engineer, your average salary, this is for mid-level, is around 111K. However, calling yourself a front-end or back-end engineer, having like a specialty, increases your pay rate. Just a little bit, but it still will increase your pay rate, and it also increases the probability that you have to get picked up by a company. Companies want a very specific kind of engineer. They want an engineer with very specific skills. So when you apply, you should be applying with, hey, I'm a back-end engineer, or hey, I'm a front-end engineer, and not trying to dabble with the in-between. With the in-between, you could tell them in interviews, say, hey, yeah, I actually have experience deploying APIs, but I'm a front-end engineer. There's no shame in that at all. It's actually great because it proves that not only do you have the skills, but you also surpass it. But as we'll talk about in a second, it's actually best on your resume to highlight only the skills that you need to get the job and maybe a little bit over. But you want to highlight very few skills and then in the interview be able to claim a lot more ground. For DevOps and front end and back end all get paid around the same amount, but cloud engineers get paid a lot more. So do AI and machine learning engineers because those are the two that are most in demand and they also take the most amount of skill. Because honestly, cloud engineering certifications are a pain and AI also can be extremely difficult to learn and to program. So having all of this, top-down knowledge is really helpful with how you market yourself. We're not going to get deep into this at all, but I also have the income rates and economic power and how much a software engineer gets paid in different regions and countries. I broke all of that down when doing this because it's cool when you're actually. Raise your hand if who here is interested in seeing offshore rates, how much it would cost or how much people get paid offshore. So if you want to hire an offshore developer, you'd want to know. Raise your hand. 2, 3. Okay, we can jump into it real quick and then we'll move on. And if you have any other questions, you could just ask me later. In North America, we have the highest pay rate hourly. Other than, I think we have the highest general hourly between Canada and the US, and that is $50 per hour for a software engineer. Here I've broken it down and based off of the Gini adjusted income. This is the Gini adjusted income, so this is basically breaking down how much is the GDP per household, per person, and then how much, and then we adjust it with the Gini score to basically adjust it for some level of error. It doesn't account for all the error out there, but this is about the average income in North America is about 50K or 49K. And so this shows you economic power based off of that of the average software engineer. So we have about, if you're a software engineer in North America, you have about 2 times the power of the average, person out there economically with how much you're earning, your earning potential. And that's really what this is, earning potential. In the Caribbean, average software engineer gets paid about 20. Same thing with the Central America. South America, it's slightly less. And then you get into Africa. Africa, it's dramatically very cheap. But I would say the rate at which a lot of African people go to college is a lot lower. I actually have statistics on that somewhere in here. Same thing with Central and South America as well. A lot lower than North America or maybe Western Europe. And we have Western Europe over here somewhere. Or here we go, Western Europe. Yeah, you can see Western Europe, software engineers, European software engineers get paid relatively similar to Northern America. You've also got Northern Europe getting paid pretty high, but Eastern Europe, that's another hotspot for offshore development. The development costs, they get paid around 23 per hour. Western Asia as well. However, if you're looking at Southeast Asia, which is another hotspot for contract work and offshore development, they get paid a lot less, around $8. And of course, these calculations have error, right? There's no way to know exactly how much these engineers and developers are getting paid in other countries. However, this is the general amount. I would always shoot for a little bit higher to be able to show your engineers and your developers that you value them. But this is essentially a great benchmark for how you pay. I would always add on maybe 25 to 40% on this, just to say, hey, look, I want you to do a good job with my application. Also, given the fact that engineers and people here get paid a lot more, everybody knows that across the world, so they'll always be expecting a little bit more than what you're going to offer them. Okay, back to our presentation. Does anybody have any questions? Yes? Does education level affect professional level? I would say masters could push you to like that mid-level category, but the distinction's not so great. A master's degree does help. It definitely helps in applications. Some larger companies only hire people with master's degrees for certain positions. But the one thing is a lot of these companies and the main thing is they want to see you join a company and grow with that company. They want you to get promoted to mid-level or senior level there, showing that you have the experience and that you just haven't worked on a university project that may not have been regulated, right? University projects are great, and especially if you have metrics to show, but you have to argue and show those metrics in case studies or on your portfolio to show, hey, look, this is exactly what I did and I know what I'm doing, right? Does that make sense? Okay, sweet. Yeah, and the main difference is university projects usually don't get deployed on a mass scale. They're usually used internally. If it gets deployed on a mass scale, that's when you're huge, you're great. So some resume tips and tricks before we jump into resume and tech stack reviews. So first one is tailor your resume for each job. This one can be kind of iffy if you don't know what should go into a good resume. But when you're creating a resume, when you find a job that you want to apply to, only highlight the skills that are important. You want to highlight the relevant skills. You want to highlight the experience that aligns with it. You can, take out other jobs. You could add in like an ellipses and show, or like a header line, right? And you could say, hey, look, there were more jobs between here and here, but I'm only showing you the ones that are relevant to this position. Focus on the keywords. So a lot of jobs will go ahead and look through the listings and put them through an applicant tracking system, which bring out and calculate the best candidates based off of keywords. So these days they just hit it with the AI and they say, hey, ChatGPT, tell me if this is a good guy for my team. And ChatGPT, based off of the keywords that it finds, will say, this person is great, or this person does not fit the bill. So, a lot of people will say, go for that crazy job that you're barely qualified for. Go for it. If you do, tailor your resume, make sure that it shows all of the matching keywords that you can possibly put in there, and focus on your strengths, right? But also focus on those keywords. Keep your resume concise and easy to read. Limit it to 1 or 2 pages. A 5-page resume, that's long. That's a lot of experience, and that shows that you've jumped around or you've moved around a lot of places. So highlight your most impactful accomplishments, your best skills, and if you have to abbreviate stuff. Add in, hey, I've got more skills than this, but these are the ones that are that apply to the job. Or you could say, hey, I have more resume experience, more jobs, but these are the ones that directly apply to what you want me to do. Use bullet points. Really you don't want big paragraphs. You want to say, hey, look, I did this, and I did this. And the real thing is you want to add in metrics. You want to add in, hey, I increased efficiency by 20%. I made our program run in 2 seconds instead of 5 seconds. My application was used by 20,000 users, that kind of deal. Use a clean layout. Keep fonts and design elements super simple. Don't try embellishing it too much. Don't get the crazy fonts out. The crazy fonts are crazy. So just keep it super simple. Your basic, I really like Avenir, or I'm a font nerd, but Inter, Avenir, those fonts are really great for just having a clean, simple, modern look. Resume tips and tricks number 3, show results, not just tasks. So quantify your impact by showing metrics, showing that you increased website traffic by 30%, you reduced response time by 15%. Give those numbers, those are important, and really highlight them. Make them in bold if you want to. That helps, Focus on your achievements, showcase where you've had successes, or improved processes rather than just generic, hey, I set up deployment, right? You want to show, again, metrics. I did this and this and this that had this response, this result. Use action verbs like I led, or I built, or I optimized, improved, or designed. Avoid passive language like responsible for, right? Like nobody wants to read a resume that says I'm responsible for teaching JavaScript and learning and managing team building exercises. That sounds long and wordy. Say, I actively improved our team collaboration by this percentage. I increased our ticket count by this percentage. I did this, and this, right? You want those active words in there. And then finally, list your technical skills and tools, but be specific about your proficiency level and apply them to what the position is. They have to be relevant to the position. If you throw in, hey, I worked on a MongoDB database in a front-end job application, yeah, it's nice, it's great, but you're crowding the resume with a keyword that doesn't matter. And honestly, a lot of resume reviewers will say, hey, look, what if they're more proficient in MongoDB than they are in the front-end tools that we need them to have? It makes it look like you are more of a jack of all trades instead of a master of one. And a lot of these jobs just want a master of one, or a master of one who could also dip his hands in other projects. So be specific about your proficiency level. Say, hey, I'm an advanced Golang writer, and that applies directly to this job. Or I know SQL, and I can do SQL in my head. I do it when I sleep. Like, I've done that before, and it's awful. I don't recommend it. And then also show your relevant certifications and how you're continuing your education. Super important, because jobs want you to be always learning, growing, even when you're off the clock. I know it sounds ridiculous and unfair, but yeah, you should be working on stuff even when you're not at work. I do that a lot. But just show that, hey, look, I thought that MongoDB was cool, so I learned it. Or I wanted to learn AWS, so I did the certification course. Mention any courses or boot camps you've completed to show your commitment. And you can show that starting from your first one. I show on my resume my first one, which was Codecademy in 2013, all the ways to, you know, your latest one, which is like AWS, how to deploy containers, something really advanced, right? Or AI basics or that kind of deal. To really show that growth. And you could, again, add in ellipses, add in, you know, I did more here and here and here, but I'm not going to show it. You should ask me in the interview, right? Right there. So real quick before we go into attendance, I have an example here of a solid resume. This came from a Business Insider article. And essentially, this was a engineer who got a bunch of interviews from all of these big FANG companies, Meta, Google, and it even said in the article that even though he got the first interview and maybe even the second one, he didn't always get the last one. It took him months, and it said that he went through, I believe, thousands of applications, looking at big tech. This was a great article to read. What he said is keep a narrow focus on technical strengths, be concise in all resume elements, less is more in this case, stand out visually, and clearly communicate responsibilities and outcomes. Outcomes being the main one here, right? And so as you can see in his resume, he shows his education up top. He uses some really nice logos. And of course, this is him coming out of college, right? He only had Ericsson on his experience belt, but he was still able to get jobs or land interviews with big companies because he was able to highlight his growth over a long period of time. He was also able to highlight the key projects and key skills that he worked with, and down here his main skills. So you can see here he's highlighting Python, Bash, C, SQL, Linux, the basics that he needs to actually get the job, right? And that's the important thing. You can highlight your skills and bullet out how you actually executed things and the metrics that you achieved, but really focus on the keywords that they want you to focus on for the job. So yeah, that's your resume tips. And so following this, we have 20 minutes to do resume review and tech stack reviews. So go ahead and scan that QR code. And then if you have a resume that you brought or a tech stack that you brought, it could be on paper, it could be in your brain, feel free to bring it to me. We're gonna hang out here for another 20 minutes, and then we're going to head down to the lobby, and I can continue talking with y'all down there. My counterpart, who was supposed to be here, couldn't show to help with the resume and tech stack reviews, so I'll try my best to juggle what I can. But yeah, And then feel free, if not, to schedule a meeting with me, and you can do that. I have business cards, and it's free. Like, I just want to help y'all out. So, yeah, fill out the attendance. It helps us improve, learn what areas y'all really liked from how we presented, and then what we can improve on. Does anybody have any questions?
Your attendance is on your card too?
No, it's not on the card. It's just up here. I do have a business card with a QR code on it as well. That's my personal information. So if y'all want that, it has links to Circle Square Labs, which is my full-service technology firm. And then also it has links to Hispanic Hackers website and all the other projects we've been working on. But yeah, thank you all so much for attending. Last thing is, it seems like everybody scanned. I forgot to add the slide in. Where is it? It is in page templates. This one. We are obliged to show this slide here. Thanking Capital Factory. Thank you so much for letting us sponsoring our meetup. Capital Factory sponsors our meetup and allows us to host meetings here. They also give us a pretty sweet co-working membership that comes along with it. So we're really thankful to them. A lot of my clients come out of here, so it's a great place to co-work, to network, and grow. And there's tons of free events like this one here. Also, future note for anybody who wants to come to future meetings, parking on the street is free. If you did park in the garage, meet me after the meeting and I can give you a parking validation. It caps parking fee at $8, which is a good price for parking out here. But in the future, feel free to park on the street. It's free after 6 p.m. on Mondays and Tuesdays. So yeah, that's the end of the presentation part of our meeting. If anybody has any questions, feel free to ask, and we will do resume and tech stack reviews. Thank y'all.
I'm gonna hang out at that table. If you wanna come over. Essentially, just bring your resume or your tech stack over here, and we can talk about it and kind of like a smaller group. Pull up some chairs. You can just go around the table. And I feel like it's best when you're collaborating with other people. You're just kind of like looking at it, like, hey, this is what I've got. But I would do is, if you see these feel like it's less important for project management. More just highlight how you communicate with people and how you communicate. I would say there's a. Have you ever heard of Open Awesome? Open Awesome is really great. I think Open Awesome is great. They do like community projects that can be data based. I highly recommend that. Okay, you're in Open Awesome. Yeah, sweet. There you go. And they're like community based projects, right? Yeah, we got a lot of. Yeah, if you're interested, give me info. Because Open Awesome is really cool. I've met with the woman who runs it. Yeah. Yeah, and she's super chill, like, very great group. I want to do a collaboration.
Do you have one that thinks around January or it just depends on the movie.
Yeah, they're always doing stuff. It's going to help you jump on one of those projects, make some contributions, and then put it in your resume. Actually, really good. If you don't mind, we're going to jump to somebody else. But if you have more questions, feel free to, we can connect on LinkedIn. And then you can always message me or send me an email. Reach out to me. Christine, right? Nice to meet you. I'm Beth.
When you have me, I'll forward your information to you again.
Oh, I think we've met before. I was like, yeah. Yeah.
Yeah.